Welcome back to the Standard Amateur Radio course brought to you by the Radio and Electronics School. My name is Ron, VK2DQ, and in this tutorial we're going to be talking about basic transmitters. This is tutorial 18 and you can test yourself on this tutorial with drill number 15. To begin with, I thought we might have another look at the block diagram we used in the last tutorial of a basic CW transmitter. And I might just run through that again with you. Won't hurt. This is a CW transmitter. We're transmitting on 28 megahertz. We have a carrier oscillator on 7 megahertz. So that's an amplifier with positive feedback and a frequency determining device on 7 megahertz. That's our carrier. We don't want to transmit on our carrier. We want to transmit on 28 megahertz. We want a low frequency carrier for stability. That's why we don't have a 28 megahertz oscillator there. And we're using a 21 megahertz oscillator to bring the 7 megahertz up to 28 megahertz. So the 7 megahertz carrier oscillator goes through a buffer. Then the Morse key. So at this point we've got Morse code at 7 megahertz being keyed on and off. Then we've got one stage of RF amplification. So here we've got Morse code at 7 megahertz at higher power being keyed on and off. Then we go into the mixer. 7 megahertz goes into the mixer along with 21 megahertz, and the frequency we want on the output, there's going to be a lot of frequencies there, but the one we want is on 28 megahertz. So we have a bandpass filter on 28 megahertz, which for CW would be 200 hertz wide, because CW, Morse code, is a very narrow band transmission. So the frequency converter, all it does is shift the 7 megahertz CW signal up to 28 megahertz. The bandpass filter gets rid of the crud, just passes the 28 megahertz. The power amplifier will bring that up to 50 or 100 watts or whatever we want for transmission, and away we go. There's our basic Morse code transmitter. While I'm at it, the simplest transmitter would just be an oscillator and its power supply, because any oscillator will transmit. In fact, the old licensing inspectors that used to come around to check if you had a TV and radio license in the days when you required them would carry a receiver with them, and they would listen to the oscillators in the TV set. And that's how they know or knew before they knocked on the door that you actually had a TV in the home. In fact, they could probably even on many occasions tell what sort of TV it is. Same thing applies to an amateur radio transceiver. The oscillators in the transceiver transmit. They don't transmit very far, maybe 20 or 30 or 100 meters, but they do transmit. So the simplest transmitter is simply an oscillator and a power supply. That wouldn't give you very much power. So a better simple transmitter would be an oscillator, a power supply, and an RF amplifier. You'll notice on the block diagram of the CW transmitter I have not shown a power supply. You never do. A power supply would be supplying power to all of the blocks on the diagram, and there's really not much point in drawing it in. Just accept the fact that there is a power supply there supplying power to each of these stages, and it's usual not to draw the power supply in. There are a couple of things that we can learn from this transmitter. Firstly, with Morse code there is a problem called chirping. It's called chirping because it sounds like a canary chirping. Chirping occurs when every time you close the Morse key, the oscillator shifts in frequency. Now normally that occurs because you don't have a buffer stage. So this transmitter wouldn't get chirping. If we didn't have a buffer, every time we closed the key to send a Morse code character, every time we send a dit and a da, the oscillator would move slightly in frequency. And that sounds a little bit like sending Morse code with a canary chirp. It's just this quick sudden change in frequency caused by the oscillator being loaded. And the solution to that, or the reason for it first, is the key is too close to the oscillator or there's no buffer there. We would never put the Morse code key in the oscillator because that would cause chirping. We put a buffer in and then we put the key in and we basically eliminate the problem with chirping. It used to be very important when radio amateurs built a lot of their own equipment, particularly Morse code equipment. If they tried to key the oscillator, they would end up with a chirping problem, and their fellow radio amateurs on air would say, look, you're changing in frequency only by a couple of hundred hertz, but you're changing in frequency every time you transmit Morse code. That is called chirping. It's undesirable, and it's caused by placing the Morse code key too close to the oscillator. There's another thing we can learn from this diagram, because there's another problem with Morse code that we need to know about, or you need to know about for your assessment. If the Morse code key turns the transmitter on and off too quickly, the transmitter will cause a problem called key clicks. To the receiver, it will sound like Morse code, and the actual Morse code key appears to be making clicks, and there also appears to be some interference above and below your frequency when you have key clicks, and there is. And the reason for this is because the Morse code key is turning the transmitter, this part of the transmitter, on and off too quickly. When I say too quickly, I don't mean we're closing the key too quickly. You can't really control how quickly or slowly you open and close the key. The key there is either closed or open. But when the key is closed, the transmitter shouldn't come up to full power immediately. It should take a few milliseconds to do that. And when the key is opened, the transmitter shouldn't power down immediately. Now this, you must understand, is in the middle of a Morse code character. So if you're sending the letter F, which is dit-a-da-dit, dit-a-da-dit, when you send the first two dits, dit-it, if the transmitter powers up and powers down too quickly, you will get key clicks, and that will cause interference. Now if you looked at key clicks on an oscilloscope, and on an oscilloscope there are two axes. The horizontal axis is time. It allows us to display waveforms, and the vertical axis is amplitude. I'll just put AMP for amplitude. The strength, the amplitude of the signal. But while I think of it, the horizontal axis is also referred to as the x-axis, and the vertical axis, the amplitude axis, is the y-axis. But on all test equipment, because on different types of test equipment it may not be amplitude and time, that's the axis on an oscilloscope. But on all test equipment, whatever the horizontal axis is, it's the x-axis, and whatever the vertical axis is, that's the y-axis, and you need to remember that. Now suppose we were going to send the Morse character A, which is dida. That's how you should write Morse code down, by the way. You should never write down a dot and a dash. That is not good. Morse code is not a visual language, it's a oral audio language. Dida is an A dot and a dash, dida. If we were to send a dida and we had key clicks, this is what it would look like on the oscilloscope. We're going to be drawing in a carrier wave, and it would the transmitter is turning on very, very quickly, and that's the transmitter sending the DIT in the A, and that's a radio frequency waveform. So we've just sent the DIT, and we're now going to send the DAR, and it's also rather squarish. See how squarish it is? And I'll explain that in a moment. That's a radio frequency waveform. In this case it would be on 7 megahertz. But you can see here, because the x-axis is time, how long did this transmitter take to come on to full power when we sent the DIT? How long did this transmitter take to come down to 0 power when we finished the DIT and opened the key? And similarly for the DAR, how long did this transmitter take to come on? How much time on this axis did it take for the transmitter to come on, and how much time did it take for the transmitter to go off? And you're going to tell me almost no time. That is key clicks. If a transmitter does that, if a transmitter comes on suddenly and goes off suddenly, comes on suddenly, goes off suddenly, that will produce key clicks, and that will produce interference to other radio amateurs. The solution is to fit in there, as close to the key as possible, a key click filter. And what that filter does, it just stops the transmitter coming on too fast and going off too slowly. A key click filter can be as simple as a capacitor, it's just a capacitor and a resistor, or it may have an inductor in it as well. It's a very, very simple circuit. But if we do have a key click filter in, I'm just going to change my pen color. If we do have a key click filter in, when we press the Morse code key down, the transmitter doesn't come on suddenly. It takes a little time to come on, like that. So there's a short rise time there. And that is what the key click filter is doing for us. Same as the decay time, it decays slowly. Might only be a few milliseconds, and there's an RF waveform still in there. And likewise with the DAR, the key click filter gives us rounded edges, gives us a decay and attack time, and that prevents key clicks, and that prevents interference, and you need to know that. Just by way of some revision and leading into where we're going with transmitters, I've drawn another CW transmitter, and this time I've made it a little bit more practical. Not that the first block diagram wouldn't work, it would work fine, but it was fairly limited in that it would not operate over a range of frequencies. So I've made some slight modifications. I've put in a doubler, and I've made this a VFO. I've left the carrier oscillator on 7 megahertz. That's providing our radio frequency sine wave on 7 megahertz. We have our buffer in to prevent chirping of the oscillator. We've got a key click filter in there. We don't normally show a key click filter on a diagram, but we do have a key click filter in there. There's the key. So at this point here, we've got a 7 megahertz CW signal, Morse code signal, that has been amplified. Pretty straightforward to that point. In fact, what we've got there is a basic transmitter. We could put an antenna on that, and we could transmit signals on 7 megahertz. Nowhere else, unfortunately. Then we go into a doubler. A doubler has the output, will have a tuned circuit in the output, and that tuned circuit in the output will be tuned to 14 megahertz. So 7 megahertz goes in. This will be a class C amplifier. So we get 7 megahertz pulses out, but those 7 megahertz pulses make this output circuit resonate at 14 megahertz. So at this point there, we now have a Morse code signal, a CW signal, on 14 megahertz. Then we amplify it again. So at this point, we end up with a 14 megahertz CW signal that's amplified, nothing else. That would be That could be a nonlinear amplifier with Morse code, or it could be a linear amplifier. We can amplify Morse code with linear amplifiers, nonlinear amplifiers, because nonlinear amplifiers distort the amplitude of the signal. They don't distort the frequency of the signal. And Morse code, it's the frequency of the rate at which the dots, the dits and the dars are coming that conveys the information, and not the amplitude of the signal. So we could use a nonlinear Class C amplifier for Morse code. So I hope you follow what's happened up until this point. 7 megahertz carrier, buffer to protect the oscillator from chirping, Morse code key filter in there, 7 megahertz CW signal here, 7 megahertz CW signal here amplified, go into a Class C amplifier, a doubler, which has got an output circuit tuned to 14 megahertz, and that doubles our CW signal to 14 megahertz at this point. Then we amplify it again, so we've got 14 megahertz coming out of that amplifier. It's just a lot stronger than what it was when it went in, going into the mixer. And we've got a VFO which can go from 7 to 7.5 megahertz going into the mixer. So if the VFO is on 7, the output will be 7 plus 21, 14 plus 21 I should say. Sorry about that. So if the VFO is on 7 and 14 is going in, we have 7 plus 14, that will put us on 21 megahertz. And if we have 7.5 going in on the VFO plus 14, that will put us on 21.5 megahertz. And then we power amplify it. I hope you understand this process of mixing. You don't have to understand what goes on in the mixer, just that when you do put two signals into a mixer, you get out their sum and difference frequencies. By the way, this power amplifier would have a band pass on it on the 40 meter emitter band, and that would get rid of all the unwanted mixing products, because mixing causes unwanted signals. These are the wanted signals, but there are unwanted signals there, so that power amplifier would have a bandpass filter in the front of it. There you go for a little bit more complicated Morse code transmitter. On screen is a block diagram of a double sideband transmitter. First time we've looked at double sideband, first time we've looked at transmitting voice. And it's not very dissimilar to our CW transmitter. The way it works is all pretty much the same. Let's have a look at it. We have a microphone, and the voice frequencies that we use in radio communications go from 0 to 3000 Hertz or 0 to 3 kilohertz. So the microphone, we'll be discussing microphones in a coming tutorial. Probably be a moving coil or dynamic microphone, or perhaps a capacitor microphone or condenser microphone in a handheld radio. And we have a microphone amplifier, and that microphone amplifier is just an audio amplifier that lifts the level of the very low level of the microphone to a higher level. Micro is from the Greek small voice, so we need a microphone amplifier. And we have our carrier oscillator, the same as we did in our CW transmitter, on 7 megahertz, but this time we're feeding our radio frequency wave of 7 megahertz, our carrier, and our audio frequency waves from 0 to 3000 hertz in the modulator. Now the modulator is just a mixer, just like this mixer over here, except when we are mixing intelligence with radio frequency carrier, we call it a modulator instead of calling it a mixer. But a mixer is exactly what it is. So when the range of voice frequencies from 0 to 3000 Hertz goes into the modulator, and it will mix with the carrier, to produce a whole range of frequencies out here, some of which we want and some of which we don't want. And the ones we want, let's get a pen. So we've got 0 to 3 kilohertz going into the modulator. And along with that, we've got the 7 megahertz signal from the carrier oscillator. Now, what that produces for us in the output of the modulator is a range of radio frequencies, and I'll draw this for you. This is frequency on this axis, and this is amplitude. This would be the axis of a spectrum analyzer, which you don't have to learn about. You need to learn a bit about an oscilloscope. So our carrier is there. That's the carrier, and that's the carrier there on 7 megahertz. So that frequency is 7 megahertz. And then we're going to have, as well as a whole lot of others, we're going to have the carrier plus the sum of 0 to 3 kilohertz. So we're going to have a whole range of frequencies here. That's our voice from 0 to 3 kilohertz above and below the carrier. So it's easier to draw it as a rectangle than to draw the radio frequencies in like that. The carrier is there, and we're going to have a band of frequencies above the carrier, and that band of frequencies is going to be 3 kilohertz wide, and it's going to be 3 kilohertz wide because that's the range of our voice frequencies. So that's going to be 3 kilohertz wide, and this one's going to be 3 kilohertz wide. And they are called the sidebands. And I'm just going to change my pen color. They are called the upper sideband and the lower sideband. The upper sideband is above the carrier, so that's the upper sideband, and it's 3 kilohertz wide. And this is the lower sideband, and it is 3 kilohertz wide. So the whole width then of a double sideband, or what most people simply refer to as AM, which is a bit of a misnomer, by the way. Double sideband is AM, but there are other types of AM besides double sideband. So in a simple AM transmitter, double sideband transmitter, we are simply taking the voice frequencies from 0 to 3 kilohertz from a microphone, amplifying them and feeding them into a special mixer called the modulator with the radio frequency carrier, this case on 7 megahertz, and that produces at the output there this signal, a double sideband radio frequency signal. All of this is radio frequencies. This is the carrier on 7 megahertz. This frequency here is 7 megahertz plus 3 kilohertz. And this frequency here is 7 megahertz minus 3 kilohertz. So they're all radio frequencies. And we've done that so that we can transmit the voice. If we just stuck the voice into an antenna and tried to transmit, stuck it straight in there, we could do it. But the antenna would be so big for that to work, we would call it a telephone line, and it would be much easier to pick up the telephone than have such an enormously long antenna. So the reason why we go through all this process is to move the voice frequencies into radio frequencies. So what we've done is moved the voice frequencies into two sets of radio frequencies called the upper sideband and the lower sideband. And with double sideband we transmit both of those. With single sideband we only transmit one of those, and we'll talk about that later on. So after we've got our double sideband, we've also got lots of other rubbish here. So we have a bandpass filter, and I've said it's plus or minus 3 kilohertz, so that bandpass filter is 6 kilohertz wide, and it's centered on 7 megahertz, so it allows this signal to pass through it. and it stops all the other mixing products that we don't want. That's what the bandpass filter does. The modulator, the mixer modulator, does the mixing, produces the carrier and the upper sideband, upper and lower sideband, produces a whole lot of other frequencies as well, but our bandpass filter, which is always, after we do any mixing, we have a bandpass filter, our bandpass filter will get rid of that mixing. So at this point here, we've got the signal that we want to transmit. Actually, we've got it there, except we've got a whole lot of other signals as well. But at this point, after the bandpass filter, we've got this signal only, and that's the one we want to transmit. We're going to amplify it. Now, if we're going to amplify this signal, we don't want the frequencies to mix with one another like they did in the modulator, or like they're going to in the mixer shortly. We don't want any mixing to occur once we've created our signal, because if we have non-linearity after we've created our signal, we're going to spoil our signal. It's going to sound awful, and it's just not going to work for us. So we must use, and this is important, we must use, after we have got our modulation, after we've created our signal, we must use linear amplification. Otherwise we are going to wreck that signal. We're going to distort it. We must use linear amplification after we have created our modulation. Because our modulation is created at a very low level, this modulator is working in the order of milliwatts. Because our modulator is at a low level, this is called low level modulation. We rarely use high level modulation today, so I'm not going to draw a block diagram of it. This is low level modulation. It's a low level modulated AM double sideband transmitter. It's called low level because the modulation is occurring at a very low level. The modulator is very early in the transmitter, and that will operate in the order of milliwatts. So this is a low level modulated transmitter. If we were to put the modulation in, so we cut that there and we take the microphone amp and we were to put the modulation into the power amplifier, and we can do that, that would be high level modulation. High level modulation if we do the modulation in a power amplifier or a high powered stage. If we do the modulation in a low power stage, it's called low level modulation. The thing to remember about high and low level modulation is that in a low level modulated transmitter, any amplification after we've created the signal must be linear amplification. So this RF amplifier here is a linear amplifier. So what we've got coming out of here, the RF amplifier, is our double sideband signal with upper and lower sideband and the carrier on 7 megahertz plus or minus 3 kilohertz. And then we go into a mixer. Now that mixer is going to give us a whole range of frequencies out here, but the sum frequencies are going to be, we add 7 to 7 megahertz, we get 14. If we add 7.5 to 7 megahertz, we get 14.5. So as we change the VFO from 7 to 7.5 megahertz, we change our output frequency from 14 to 14.5 megahertz, because we're just summing the variable frequency oscillator with our signal in a mixer to produce that output. And of course there would be a band pass filter in that power amplifier, getting rid of any mixing products that we do not want. That's low level modulated double sideband transmission. Now, one thing you may have to do in your assessment is identify the waveforms from a double sideband or single sideband transmitter. And what I've done is put up some of the waveforms that a double sideband transmitter will emit Suppose that we were transmitting, but we're not speaking into the microphone. If we were not speaking into the microphone, remember before I drew what we get at the output of the modulator. We get the carrier frequency and we get an upper sideband which is 3 kilohertz wide. We get a lower sideband which is 3 kilohertz wide, and that's because of the voice frequency. Good idea to remember that in double sideband the bandwidth of the signal is twice the highest voice frequency. In single sideband the bandwidth, because we're only using a single sideband, is equal to the highest voice frequency. So double sideband is 6 kilohertz wide and single sideband is 3 kilohertz wide because of that. Double sideband is twice that, single sideband is equal to that. You need to remember that. So let's suppose we were not speaking, we just transmitted and didn't put our hand over the microphone and didn't speak. Then we wouldn't have an upper sideband or a lower sideband. They'd be gone, they wouldn't be there. We would just have a carrier, and on an oscilloscope that's what we would see. And that's a radio. There's lots and lots and lots and lots of sine waves in there. You can't see them because they're all so close together, but that's a 7 megahertz sine wave. So that's the radio frequency carrier as it would be seen on an oscilloscope. This axis is time on an oscilloscope. It's the x-axis, and this axis is amplitude of the signal, and that axis is called the y-axis. If we modulated our transmitter to 100% modulation, we would see the top one. This is 100% modulation. It's 100% because of the shape of these valleys, these hills and troughs. If we were over 100%, if I just drew over 100% here, it would come down and you would have a flat line, quite a distinct flat line. There would be a flattening of these valleys, and that would be over 100% modulation. But I'm just going to take that back off. That's 100% modulation. Oh, I don't know why I just did that, because underneath I've got a diagram of over 100% modulation. I was trying to show you the flattening between the cycles there. That is over modulated, greater than 100%. Forgive my writing. That's over modulated, that's 100% modulation, and the bottom one is 0% modulation. And you may have to identify one of those for your assessment, so we'll put some of them in the drills for you. Well, I think we've reached the point where we can go through some trial assessment questions with you. And if I've missed anything, I will pick it up when I go through those questions, but I don't think I have. Let's have a look at some trial questions and see what we've missed. I've just put that back up on the screen for you so you can see it. I think it's a good idea to draw that or screen grab it and print it. If you're using Windows 7, you can use the snipping tool and just snip that off the screen and print it. A really good idea to print these block diagrams, and then you can look at them in your leisure and see if you understand them. I almost feel like going through this with you just quickly once more, because I know it's that important. This is a double sideband AM transmitter, and I'm just going to do this quickly. Our voice frequencies from 0 to 3 kilohertz go into the microphone. They are amplified by the microphone amplifier. The carrier is on 7 megahertz, generated by the carrier oscillator. That goes into the modulator, which is just a special type of mixer. The output of the modulator will contain the carrier and the upper sideband and the lower sideband, and they are all radio frequencies. That's the lower sideband. That's the upper sideband. There's no advantage on either sideband, by the way. Radio amateurs use both, but commercially everyone uses upper sideband only because there's no advantage between upper and lower sideband. The bandpass filter gets rid of the crud that's here, so it just gives us a nice clean double sideband full carrier signal coming out there. That signal is then amplified in a linear amplifier. We must use linear amplification after we've done modulation. This is low level modulation. We're then putting a 7 megahertz plus or minus 3 kilohertz signal into the mixer and mixing it with a VFO that ranges from 7 to 7.5 megahertz. That gives us an output there of 14 to 14.5, and the power amplifier just boosts up our power ready for transmission. Alright, I think I've bored you enough with all of that. Let's have a look at some sample assessment questions. Let's have a look at section 15 of your sample questions, which you'll find in your document folder, doc folder of your DVD. 15.1. A simple telegraphy transmitter may consist of. Now they have to use the word may here because there are different combinations of simple transmitters that will work. But one thing you're going to need for sure if you're going to transmit is that you're going to need an oscillator, because it's the oscillator that produces the radio frequency energy. You're also going to need a power supply. They're absolute necessities. So the simplest transmitter would just be an oscillator and a power supply. But a better transmitter would be an oscillator, power supply and an amplifier, answer B. And that would just be a telegraphy transmitter. 15.2, similar question. In its simplest form, a transmitter may consist of. Well, it's not A because there's no oscillator. It's not B because there's no power supply. It's C because you have a power supply and an oscillator. And in the previous question you had a power supply, oscillator and an amplifier, which is even better. Question 15.3. The purpose of the buffer amplifier stage in a transmitter is to provide a constant load on the oscillator. Moving on, let's look at question 15.4. We need to talk about this one a little bit because this one is about bandwidths, and I knew this one was coming up, and we haven't really talked about bandwidths a great deal, which is the width that a radio frequency signal takes up in the spectrum. Let's read the question and answer it first. 15.4. The type of transmission which takes up the least bandwidth in the radio spectrum is CW, Morse code. Now what I'm going to do is type these in. We're going to be talking about these later. I hope you can tell me the bandwidth of single sideband and double sideband after looking at the last tutorial, number 18. Morse code, the bandwidth is about 200 Hertz. So it's a very narrow band signal, and that's why Morse code is so good at communicating in noise, because the narrower the bandwidth of the signal, the less noise you have in the receiver. Single sideband is 3 kilohertz. Double sideband, I hope you're saying this in your head because we just did it, is 6 kilohertz. I better put a HZ on the last one. So 200 Hertz for CW, 3 kilohertz. That's because voice frequencies range from 0 to 3000 Hertz. That's why the bandwidth of SSB is 3 kilohertz and double sideband 6 kilohertz. FM, much wider bandwidth, 16 kilohertz is a typical bandwidth of an FM signal. But there are exceptions to that. There is narrow band FM, which is narrower than 16 kilohertz. But they're the ones you probably should remember, particularly the double sideband, single sideband and CW. 15.5. This circuit diagram. Now I doubt very much if you're going to have to identify this circuit diagram, but you can see the key. That's the Morse code key, and what this is the key click filter. You do need to know about the key click filter, but I doubt if you're actually going to have to know how to identify that diagram. So That is the circuit diagram of a key-click filter. Question 15.6. Key clicks can be suppressed by, well, there's our key-click filter, inserting a choke and a capacitor in the keying circuit. Actually, sometimes just a resistor and a capacitor is more than enough. You don't have to insert a choke, but you can. So a key-click filter, remember, stops our transmitter from coming on too quickly and going off too quickly when we send the dits and dars. Question 15.7. A telegraphy CW transmitter should be fitted with a key-click filter in order to shape the leading and trailing edges of the keyed transmitter output waveform. That's a convoluted way of saying we have to increase the attack and decay time of the leading and trailing edges of the Morse code signal. That's what, and we explained that. I'm pretty sure I explained that in the tutorial. 15.8. Chirps in a telegraphy CW transmission are most likely to occur if keying is applied to the oscillator. We should never put the Morse key on the oscillator. We should have a buffer after the oscillator and then have the Morse key. Chirping is when the oscillator is being pulled off frequency because you're trying to pull too much power out of it and you don't have a buffer stage. 15.9. A form of frequency instability which occurs when a CW transmitter is keyed produces chirps. While we're at it, if an SSB transmitter is overmodulated, it causes splatter. And splatter is a technical word. And that is an answer to one of your exam questions, I know. So if you overmodulate an SSB transmitter, you cause the linear amplifiers in the output stage of the transmitter to become non-linear. You then get unwanted mixing. That unwanted mixing causes splatter, which is interference above and below your signal. 15.10. In a telegraphy CW transmitter, a key-click filter is normally placed. Let's have a look at our options. Where would we put a key-click filter? Well, I don't think we'd put it at the antenna terminals. I think we would put it as close as possible to the key or keying relay, is the answer. Certainly wouldn't put it in the transmission line. Certainly wouldn't put it in A. Someone's got a sense of humour with making up these questions. 15.11. This is an oscilloscope type 1 where you've got to identify which of these waveforms is the higher frequency than the other. Remember, the horizontal axis is time, the x-axis, the vertical axis is the y-axis is amplitude. So the higher frequency signal will have more cycles in the screen than the lower frequency one, because the time on the horizontal axis is the same time for both of them, yet B is able to scribe out several sine waves compared to A. So B is definitely more higher frequency than A. So B has a higher frequency than A is the correct answer there. (15.12) This RF waveform, as seen on a cathode ray tube, that's an oscilloscope, represents this one here. It's a sine wave, but you can't see the sine wave because there are so many of them and they're so close together. It's a radio frequency sine wave. It's the carrier. The unmodulated carrier would look like that on an oscilloscope. If we were using a double sideband AM transmitter and we didn't speak into the microphone, we wouldn't have sidebands, we'd just see the carrier. 15.13, this waveform represents a... There's no correct answer. Alright, I'll fix that straight away. It's a 100% modulated AM transmission. (1514) Testing a telegraphy transmitter for key clicks would most effectively be done, well, you'd have to use an oscilloscope. There's no other way. 1515, the bandwidth of an amplitude modulated AM signal is determined by, remember it was 6 kilohertz wide, and remember the frequencies that went into the microphone, 0 to 3000 hertz. A double sideband signal is twice the bandwidth of the modulating audio. So let's have a look. The bandwidth of an amplitude AM signal is determined by the frequency of the modulating signal. If the modulating signal goes up to 3 kilohertz, which is the case with amateur radio, then a double sideband signal is 6 kilohertz wide, and a single sideband signal is 3 kilohertz wide. Need to remember those. And just to be complete, a CW signal is only 200 hertz wide. 1516, a bandwidth question again. Compared with an amplitude modulated signal, a single sideband signal modulated with the same audio frequency occupies approximately half the bandwidth. 3 kilohertz instead of 6 kilohertz. 15.17, if the carrier is amplitude modulated by an audio signal of 1 kilohertz, the bandwidth of the transmitter's modulated signal will be, well, it's modulated with 1 kilohertz rather than up to 3 kilohertz, and it's amplitude modulated. It doesn't say, the question doesn't say whether it's double sideband or single sideband. Well, let's assume that let's assume they're talking about double sideband, so I'll modify that question. I would assume though we're talking about double amp. If they just say amplitude modulated, I presume that the examiner's just talking about double sideband, because if they wanted to talk about single sideband, they would have said single sideband. So the bandwidth's going to be twice the highest modulating audio. That's going to be 2 kilohertz. 1518, overmodulation of an SSB transmitter will cause splatter. Overmodulation occurs when you turn the microphone amplifier up too high and you cause the power amplifier in the transmitter to become nonlinear. It then becomes a mixer. It then mixes the sidebands again with the carrier to produce other frequencies which are transmitted and can cause interference. So overmodulation is bad. Never more than 100%. 15.19. A transmitter is more likely to cause interference to broadcast and television reception when it is overmodulated. Should never be more than 100% modulation. The transmitter should never be overmodulated. 1520, a carrier wave is overmodulated when the percentage of modulation is greater than 100%. 1521, overmodulation of an AM transmitter will produce spurious emissions, not parasitics. Parasitics are not caused by overmodulation. Parasitics are caused by stray circuit inductance and capacitance forming unwanted tuned circuits. So spurious emissions are caused by overmodulations. Parasitics are a fault within the radio. Overmodulation is a fault with the operator for turning his modulation up too high. 1522. When low-level modulation is applied to a transmitter, it is the final stage is modulator. That's not low level. The final stage, that's not low level. The modulator is bias class C. That's a nonsense. Class C can be used throughout the transmitter. That's not true because they're non-linear amplifiers. All stages after modulation must be linear. Once you've created the modulation from that point on, you must use linear amplification with a low level modulated transmitter. And that's what we had up on the screen in the last tutorial. 1523, in an AM transmitter, low level modulation is usually applied to stages before the power amplifiers. Low level modulation has to be applied to a low power stage. 1524, the transmitter stage which draws the most current is usually would have to be the power amplifier. 1525, when low level modulation is applied to a transmitter, all stages after modulation must be linear. That looks like a double up. Sorry about that. Won't hurt. It's a little bit of a reinforcement. Does no harm. I've got two 1525s, that's probably why, and I've forgotten to take one out. I'll fix that on your sheet. 1525 again. With amplitude modulation, the degree of modulation should never exceed 100%. That looks like another double up. I'll sort that out, don't worry about it. And this looks like the last one. I may put extra questions in on your drill, by the way, that I don't cover here. That's just because I've found one or two that I think might help you. So don't be surprised if you do come across an extra question every now and then that I don't go through on the sheet. 1526. When signals are converted using mixers in a transceiver, well, every time we use mixers, we get what we want as one of the mixing products, but we also get a lot of rubbish as well. So unwanted frequencies are produced. There you go. I'll see you back in the next tutorial, and I hope this is all making some sense to you. I hope you're enjoying the course. If you do have questions, don't hesitate to drop me an email at ron@res.net.au. Please quote your question. If you're going to ask questions from the question sheet, the sample questions, don't refer them by reference. Send me the question you want me to comment on. And it helps if you send it in a Word document as well as an attachment on an email. It allows me to put some photos and sound and things like that in it if I need to. Alright, well thank you for that. Thanks for listening. I'll see you back at the next tutorial. Cheers for now. This is Ron, VK2DQ.